Hello everyone and welcome to CAD Chemistry tutorials. This is the third part in the series of numerical simulation of 2D steady state heat conduction. Here in this video we are going to develop a MATLAB code in order to simulate the steady state heat transfer inside a 2D domain. In the previous videos we have discussed about the formulation of governing differential equation, discretization of domain, and how to convert the governing differential equation into algebraic equation. Now here in this video we will use the algebraic equation that we have derived in the part number 2, and we will use the same equation in order to find out the temperature inside all the grid points in the domain. So here you can see the same equation that is implemented. Now so let's run this code and see the results of our MATLAB code. And here you can find the result of the simulation on the screen right now. Now here you can see that the left wall of the domain is maintained at a constant higher temperature of 120 degrees centigrade, and remaining three walls of the domain are maintained at a constant lower temperature of 40 degrees centigrade. So by using the algebraic equation that we have derived in the earlier videos and by using a MATLAB script, we can do a simulation of 2D steady state heat conduction. Once we get the results from the simulation of our MATLAB code, we'll validate the results of our MATLAB code with the results from the ANSYS Fluent, and that we will do in the next video. So now let's begin with the development of our MATLAB code. So let us first close this figure. Now here you can find here that in the command window you can see some digits. So we'll discuss next what are these digits. So first what we'll do is we'll clear all the calculations in the command window. So we'll type here CLC and press here enter, so that all the calculations that are performed in the command window will be erased. Along with that, here in the workspace you can see here that there are number of variables and their values. So we'll also clear these variables along with their values. So in the command window we'll type here clear all and press here enter. So here you can see that we have erased all the workspace variable as well as we have cleared all the calculations in the command window. So here if you see this code, you can find here that we have divided our code into main four parts. The first part is the geometric parameter. The second part is boundary and initial condition. The third part is computation, and the fourth part is the plotting of results. So here in this video we'll see each and every step in detail. So let us first create our new MATLAB script. So first we'll clear all the variables and we'll clear all the calculation. So if in MATLAB there are any previous calculation and previous variables, we can always erase all those variable and calculation. So first we'll enter here CLC to clear all the calculations in the command window, and second we'll clear all the variables and their values. After clearing the command window and workspace, we'll start our code. So the first part is the geometry. So here first we'll insert the percentage signature. So all the values or all the characters that are written after the percentage sign will be considered as a comment, and this comment will not take any part inside the calculation. So we'll enter here 2% signature to define a section. Then we'll make one space and then we'll write here name of section, that is geometry of domain. Now in the geometry we are having length and width of the domain that you can see over here. So let's enter here W as a width of domain and let us take it as a 1 meter. Now here we'll give every variable a comment, so that in future if we have to find any variable then we will not have any confusion. So in comment we'll write here that width of domain along with its unit, that is in meter. The second is the height of domain, that is denoted by h, and let us take it also as 1 meter. So here we'll comment it as height of domain, and that is also in meter. After specifying the width and height of the domain, we have to discretize the domain, that is we have to divide the domain, and for that we have to divide domain in vertical as well as horizontal direction. So let us say that we are creating the nx number of grids in x direction. So let us take nx, that is equals to, let us say, 51. So nx is nothing but number of grids in x direction. In the similar fashion, we will define ny as a number of grids in y direction. After defining the number of grids in x and y direction along with the length and height, now we can find the value of dx, that is of small elements of here, that you can find here dy as well as dx, and we have seen that dx is nothing but width divided by number of grid point minus 1. So let's incorporate this equation into MATLAB, and let us say dx equals to width divided by number of grid point in x direction minus 1, and let's comment here that width of element, and that is also in meter. In the similar fashion, we can define dy as height divided by number of grid points in y direction minus 1, and let us call it as the height of element, that is also in meter. Now these are the details that we require for the geometry of our domain. So after defining the geometry of domain, now it's time to define the boundary as well as initial condition. So we will create another section by inserting double percentage signature, then we will create one space and then write it as a boundary and initial condition. So in the boundary as well as initial conditions, let us first talk about the initial conditions. So initial conditions are nothing but when we are starting the simulation, then we have to specify the initial temperature of the domain. So using the MATLAB, we can also initialize the temperature of the domain. Now here we have defined that number of elements in x and y direction as nx and ny. So basically in our domain, we have domain with the grid points nx and y. So we'll define the temperature T, and let us say the initial temperature of the domain is 25 degrees centigrade. So here we'll enter 25, then multiply, then we'll enter here once, and inside bracket we have to define here the dimensions of the matrix, that are nx and y. So what this syntax tells us, that we have defined an array with name of T, capital T, that is temperature. Once we'll assign all the values of the elements as 1, and after assigning all the value as 1, we are going to multiply all the elements of the array by 25. So if we multiply 1 by 25, it will be 25. So basically we have defined an array named as a T. The elements of array are nx and y, and all the elements are having value of 25 into 1, that is 25. So initial value of all the grid point inside the domain is 25. So let us type here the array, or let us say temperature array. And that is also in degree centigrade. Now this is the initial condition of our domain that tells us that initially the domain temperature is 25 degrees centigrade. Now from this slide you can see here that we have divided all the grid point into different classification. So this is the left wall, this is the top wall, this is the right wall, and this is the bottom wall. So these are the boundary grid points, and first we'll decide all the boundary grid points. So let us start with the left wall. So here you can see that from y grid point of 2 to ny minus 1, we have all the grid point at a temperature of TL, let us say TL as a left wall. So before assigning the temperature, let us first define the four temperatures. First one is the TL, that is left wall temperature, and we'll assign a value of, let us say, 120, and we'll comment here that left wall temperature, and that is in degrees centigrade. In the similar fashion, we'll define the right wall temperature also, and with the value of, let us say, 40 degrees centigrade. That is also in degrees centigrade. The top wall temperature is also, let us say, 40 degrees centigrade. And finally, the bottom wall temperature as a 40 degrees centigrade. So after defining all the four wall temperatures, now we'll assign these values to the grid point, to the respective grid points. So from here you can find here that when this first column is having index I value 1, then this is having index I value 2, this is having 3, and ultimately it is having index I as nx. So if we have to specify the left wall temperature to all these red color grid point, then its I index will be 1, but j index will vary from 2 to ny minus 1. So all these grid points are having value of TL, that is 120 degrees centigrade. So to define all these grid point with a specific value of TL, we can write here syntax as temperature T. Now into bracket our I index, or let us say in x direction, the index value is 1, but in y direction it varies from 2 to nx. So here we can give all the grid point in a single short value by writing 2 colon ny minus 1, then we'll bracket over and assign value of TL, that is left wall temperature. So what it will do is that it will assign all the elements of the array temperature T. Now what are those elements? Those elements are having index 1, I index 1, and j index from 2 to ny minus 1. So basically this will assign the value of TL to all these grid points that are shown by the red color. So in the similar fashion we can assign the values of this top wall also, and for that we have to specify here the array name as a temperature T. Now here in this case the x will vary from I equals to 2 to nx minus 1, but y will be ny. So we can specify here that x will vary from 2 to nx minus 1, but y will be ny, and here the value is tt, that is top wall. In the similar fashion we can assign value to this blue color grid point with the value of right wall temperature. So here for this grid point the x or I index will be nx for all the grid points, but j index will vary from 2 to ny minus 1. So here temperature variety, and here the x will be nx, that is same for all, but y will be from 2 to ny minus 1, and we will assign the value of right wall, that is TR, and in the end we will assign value to this bottom grid point, and this bottom grid points will vary for I index from 2 to nx minus 1, but in j it is 1. So let's say here T of 2 to nx minus 1, and for the j it is 1, and the value is TB, that is bottom wall. So after specifying the values of this grid point, now we have to assign value to this corner grid point. So in corner grid point you can see that these corner grid points are shared by the left wall as well as bottom wall. So generally what people are doing is people are assigning the values of this grid point as average of these two temperatures. So for this grid point, we can assign the value of temperature, that is average of TL plus TB. So here, and this grid point is having index I and j as 1 and 1. So let's say here temperature T, and I index is 1 as well as j index is 1, and that is having the value of average of left and bottom wall. In the similar fashion, we can assign here this grid point as a value of right wall and bottom wall, and here the I index is nx and j index is 1. So here I index is nx and j index is 1, and it is having average value of T right plus T bottom. In the similar fashion, this grid point is having index I1 and index j and y, and having value of average of left as well as top wall. And finally, for this corner point that is having index I of nx and index j of ny, it is having the value of average of top as well as right wall. So here temperature for nx comma ny and the average temperature of right wall as well as top wall. So here you can see that this is the initial condition of our domain. So by this statement we are telling the MATLAB that all the grid point of the domain are initially at 25 degrees centigrade. Now these are the boundary conditions. So in order to specify the temperatures, first we are defining the left, right, top and bottom wall temperature, and here we are using all this temperature to define the boundary conditions for our domain. So these four statements are used to define the wall boundary condition, and these four statements are used to define the corner boundary conditions. So after defining the boundary and initial condition, we can go for the computation. So we'll create another section and we'll give it name as a computation. So inside computation, what we are doing is that we are trying to get the temperature distribution inside the domain, and for that we are using the algebraic equation that we have formulated in the previous video. So here, as we keep on calculating, the values of the temperature inside the grid point will evaluate, and after some iterations we will get the steady state, so that there will not be any change in the temperature of the grid points. And for that purpose, in order to know that whether the convergence is reached or not, we are using one variable that is called as error. So we'll find at the end of each iteration, we'll find the error and we'll try to compare the error with one predefined value, and we'll see whether error is greater than that predefined value or less than that value. Once the error comes down to that predefined value, we'll stop the iteration and we'll assume that the convergence has been reached. So let us first define that variable and we'll name it as epsilon, and we'll give it value as a 10 to the power minus 3 initially. And initially we will give the value to the error as a 5, so that initially you have to give the value that is greater than the epsilon, otherwise there will not be any calculations. So after defining the epsilon as well as error, now we have to create the nested for loops in order to carry out the computation. So first we will try to implement the equation that we have derived in the previous video, that is the algebraic equation. So here you can notice that in our domain we have to start with the first row, then second row, third row, fourth row up to ny row, and in each row we have to perform the calculations for I equals to 1 to nx. So let us say that for j equals to 1 we have to perform calculation for I equals to 1 to nx, for j equal to 2 I equal to 1 to nx, and in the similar fashion for j equals to ny, we have to perform calculation for I equals to 1 to nx. So basically we have to use the nested for loop in order to carry out the computation for all the grid points. Now here you can see that we have already defined the boundary conditions of these grid points, so we don't need to perform the calculation for this boundary grid point because the value of temperature of these boundary grid points will not be varied. So we have to perform calculation for these inner grid point that are shown by this green color. So if we consider only this domain that is shown by these green dots, then it will start from j equals to 2 to j equals to ny minus 1, and in x direction it will vary from I equals to 2 to nx minus 1. So first we have to cover all these interior grid point, and for that we will use two for loop. So let us say for first for loop we will vary the indices j, and that is from 2 to ny minus 1, and inside the for loop for the index j we will use another for loop for the index I, and that is for I equals to 2 to nx minus 1. So basically it will cover all the grid points that are shown by this green color. So we have to perform the calculation for these green grid points, and here we know the algebraic equation from our previous video, and we have found it as average of all the four adjacent temperatures. So T of ij is nothing but T of I plus 1j plus T of I minus 1j plus T of ij plus 1 plus T of ij minus 1, and entire term divided by 4. So in the similar fashion we have to apply the equation over here. So T of I comma j is nothing but, first we have to sum all the grid point, all the neighborhood grid point. So T of I plus 1 j plus T of I minus 1 j plus T of I j plus 1 plus T of I j minus 1. So these are the four neighborhood grid point for the grid point ij, and we have to take average, so we have to divide it by 4. So this is the equation, that is the algebraic equation, and now we will end this first for loop by typing here end, and we'll close the first for loop by typing here end. So this will basically perform the calculation, and it will find the temperature of all the grid point that are shown by this green color. So basically it will find the temperatures of the interior grid point. So how it will know that whether the convergence has been reached or not? So here, before it will go to the calculation, we will assign the temperature values to one variable, and we will name it as a T old. So that is the old temperatures, and we will assign the value of T to the old. So once the array T will give all its value to the array T old, after giving its value to the T old, it will find the new value T. So the value of T old and T will be different. So after performing certain number of iterations, the difference in the value of T old and T will decrease, and after some iteration we will find that this value is very small, and we can say that the convergence has been reached. And for that we have to find error at each and every iteration. So we will define error here as, so first what we will do is that we will make a difference between the T and T old. So let's see here T minus T old. After finding the difference, what we will do is we will make square of all the elements of this T minus T old, and then we will make summation of all those squared elements. So the basic syntax is sum square, that is SUM SQR. So what SUM SQR will do is it will first find the difference between the corresponding element of T and T old. So what it will do is it will find the difference between T11 and t old 11. Similarly, t22 and t old 22, t12 and t old t12. So it will find the difference between the corresponding elements. After finding the difference, it will make the square of those differences, and after creating the square, it will sum all those squared value. And we have to make the square root of those value. So here we will type as sqrt of all those values. So basically here we have found the root mean square value of t minus t old, and we will assign the value to the variable error. So this step will continuously assign the value of t to the variable of t old. It will find new value of t, and then it will find the error. So this calculation keeps on going until the convergence reach, and we can stop by using the while loop. So while loop will make the decision when to stop the calculation. So inside while we have to give the condition for when to stop the calculation. So while the epsilon, or let us say while the error is greater than the epsilon, then it will perform the calculations, and once the error will be less than epsilon, the calculation will not be performed and it will stop the calculation. And let us end here the while loop. Now we'll select the entire code by using Ctrl A, right click and select here Smart Indent. Now here, in order to have a look at the calculation process, we will define one variable, that is iter, and let us define value of 0. And here, in order to check how many iterations are performed, we will display the number of the iterations. So for each calculation, the iteration value will be updated. So here we will enter iteration as iteration plus 1. So for each calculation, the iteration number will be increased, and it will be displayed by using this display command, and enter here iter, that is the name of variable. So it will update the number of iteration and it will display that number. And here we can also show the error, so that we can come to know that now how many iterations are remain. So here we can display the error also by using the disk command only. So let us understand how this code will work. So initially the iterations are 0, and first it will check that whether the error is greater than epsilon or not. So obviously we are going to perform the calculations, so initially we will assign the value to the error that is greater than epsilon, so that the calculation will go inside the while loop. Once it goes inside the while loop, it means that it will perform the calculation, so that the number of iterations should be increased. So for each calculation, the number of iteration will be increased by 1, and here it will be displayed by this command. Now what it will do is, it will assign old values of t to one variable, that is t old, and then it will find new value of t. Once it will find the new value of t, it will compare the new value of t with the old value of t, and it will find the root mean square of t minus t old, and it will check that whether the difference is very small or large. So when the difference is very small, then we can observe that the steady state has been reached. That means there is no difference with respect to iterations, and we can expect no further difference while performing the calculations further. So we'll stop the calculation when error is less than epsilon. So this is basically the calculation step, and once we do all the calculations, then we will be having the value of temperature at all the points inside the domain. So now after performing the calculation, we have to plot the results. So we'll create another section and we'll name it as a plotting the results. Now in order to plot the results, now we know here that the dx we have found from the number of element in x direction as well as width. So our domain will start from x equals to 0, and the length is W, that is of 1 meter, and we have divided it into 51 number of elements. So here each element is having the value of dx. So I will create one new array, that is array name x, and array will start from 0. Now each array element will be having increment of dx from the previous element up to w, that is the width of domain. So that is nothing but the width array. We will call it as width array, and each element is having unit of meter, so we'll enter here in meter. In the similar fashion, we'll create another array for the vertical direction and give it name as y array, and here y will also start from 0. It will create increment of dy and up to capital H, and we'll name it as a height array, that is also in meter. Now after creating both the arrays, now we are going to plot the results using the contour plotting. So the syntax for plotting the results of a 2D array by using the contour is, first we'll define the contour. So before that we have to define the color map. So we'll define color map, and that is as a Z, and after that we have to define the contour. So we'll enter here contour, and in bracket the value of variable of the first index, that is x direction. So in contour we'll first enter x. The second element represents the y direction, so we'll enter here y. Now here we'll enter here transpose of t to get the results in the way we have entered the value. So we'll enter here t prime, that is nothing but the transpose of t. So these two lines will plot the contour plot in the new figure. Now after that we'll give it title as well as x and y axis name. So in order to apply title, we will type here title, and inside title we can give it name here as a temperature distribution. In the similar fashion, we will give it x label, and we will type it as width, and that is in meter. For y label it is height, that is also in meter. So this is the entire code that we have proposed to develop. And now let's try to run this code by simply clicking on this run button. So till now we have not saved this code, so we'll give it name as a steady state heat conduction, that is for 2D domain, and let's save it. After saving it, it will start the calculation, and here you can see that it has performed 2180 iteration, and the value of the error is 9.96 10 to the power 4, that is less than 10 to the power minus 3. So once the value of error is reached below 10 to the power minus 3, the calculation has been stopped and you can find the results of the calculation. Now here we'll add another line for the color bar. So we'll enter here color bar. So you can find here that which color represents which value. So again we'll run this code and you can find here the results. From the results you can see here that this dark red color represents the value 120, that is highest value, and you can see here that the left wall of the domain is assigned the highest temperature value. Another three walls are assigned the value that is corresponding to this dark blue color, and that is of 40 degrees centigrade. And here the 0 represents the start of x direction, and it will go from 0 to 1 meter in x direction. In y direction also it is go from 0 to 1 meter. So here this is all about the development of 2D steady state heat conduction. Now here if you increase the convergence criteria, that is, if I enter here, let us say epsilon value is 1 e to the power minus 4, that is 10 to the power minus 4. So in order to bring the values closer, the value of t and t old, it has to perform more iterations. So what basically will happen is, here for the epsilon value of 1 e to the power minus 3, the number of iterations were 2180, and for the convergence criteria for 10 to the power minus 4, it has to perform more iteration than 2180. So now let's run it and see the number of iterations. So here you find that initially the number of iterations were 2180 and now it is 2762. So when you increase the convergence criteria, or when you restrict the difference between the updated value and old value of temperatures to the small number, then it has to perform more number of iterations, but the accuracy of the solution will increase with lower value of epsilon, or let us say lower value of RMS. So here in this video we have tried to develop the MATLAB code for the steady state heat conduction inside a 2D domain, and here you can see the results of that simulation. In the next video we will perform the same simulation using the ANSYS Fluent, and we will try to correlate, or we will try to validate our results with the results from the ANSYS Fluent. I hope you enjoyed this video. If you like this video, then please hit on the like button, share it, and subscribe to this channel CAD CAM CE Tutorials. Thanks.